In this video, we're going to talk about reliable messaging with RabbitMQ. RabbitMQ is a message broker. So here we have the message broker. And the broker's main function is to take messages from some publisher and then forward that to a consumer. Now the broker stores these messages internally inside some queues. One of the things about the message broker or a messaging system in general is that you can locate the publisher and the consumer in separate physical hardware. So for example, I can locate the publisher in machine 1, the broker in another machine, and finally the consumer in another machine as well. Okay, so once you have this system in place, you can actually scale out your computation by just adding more machines. To summarize, there are 3 components to a messaging system. First, you have the publisher, and then you have the consumer, and you have the message broker, which manages a series of queues. One of the key features of a messaging system is its ability to store and forward messages. What I mean by that is sometimes the publisher can send messages to a queue, but there are no consumers available to consume those messages. Now, it is the responsibility of the message broker to store those messages inside its queues. So in this example, I have a publisher, but I don't have a consumer. So if the publisher starts sending messages to the message broker, it's going to store them in a queue. So if I send message 1, right, it was going to store message 1, message 2, message 3, message 4, and message 5. Now if the publisher goes away, right, those messages will persist inside the message broker until a consumer is available to consume those messages. So let's say later on a consumer does come up and starts to dequeue those messages, then at that point, that's when these messages will be removed from the queue in the order that they are put on the queue. Another feature of the messaging system is its guaranteed delivery of messages. If you follow their protocols, then you are guaranteed that no messages will be lost. Now, in order to do that, what happens internally is that if you, from the publisher's perspective, if you send a message to the message broker, it can give you a message confirmation that it actually was stored successfully inside the message broker. Now, when the messages go to the consumer has to act on this message. Act is for acknowledgement. Right? It has to acknowledge that the message was processed successfully, and only at that time will the message get removed from the queue. Right? And this is how the messaging system can guarantee you a reliable message delivery system. Now let's take a look at how the system handles failures in different scenarios. First, let's look at the publisher. right? So if the publisher tries to send a message to the message broker, and at this point, assuming there's some network failure between the publisher and the broker, so what happens to the messages, right? If at one point the message could be stored in the queue, and you may not have received a confirmation, right? So let's say you didn't get the message confirmed that it was actually stored inside the queue. So this means that the message was actually delivered, but the publisher doesn't know that it was delivered. Now it's up to the publisher to store those messages and send them to the message broker at a later time, right? So let's say that it didn't get the confirm and it retries and resends the message at a later time, right? And it tries to send message 1 again, right? So what that means to the message broker is that you can actually have duplicated messages. Okay, the second, so this means that your application must be able to handle duplicated messages. The second scenario is when the messages are being consumed by the consumer, right? And the messages will be stored inside the queue until the consumer can act on those messages. So normally you would only act after you successfully process those messages, right? So the consumer is supposed to send an act back to the message broker. Once the act is received, it will remove those messages from the queue. So let's assume that the consumer did get the message 1, but the act failed for some reason, right? So that means that message 1 was processed, but since we didn't get the act back, the message 1 is still inside the queue. Now later on, let's say there's since this consumer crashed for some reason, another consumer comes alive, and then it starts to dequeue. So that means it will get message 1 again, right? And if it acts that message, then that message can be removed from the queue. Right? So there is a potential for duplicated messages to be processed, and that is known as a redelivery. Okay, and inside the message there's actually a flag that is set to let the consumer know that this message was redelivered. Another great feature of any messaging system is the ability to add multiple consumers to a queue. In doing so, you are able to process the messages in parallel. So let's take a look at an example. Here in this picture, I have a producer. So let's assume that this producer publishes 4 messages to a queue. So I'm going to have message 1, message 2, message 3, and message 4. If you have more than one consumer attached to a queue, the messages will be dispatched to the consumer using a round robin algorithm. So in a perfect situation, the first consumer is going to get message 1, and then the second consumer is going to get message 2. Now, once the consumer finishes with message 1, the dispatcher is going to assign that consumer the next message, which is message 3, and then message 4. So in this scenario, we actually cut down the time to process all the messages by half. And if you want to scale out, you can actually add more than 2 consumers. say, as an example, if I add an additional 2 consumers, then I can actually cut down the time to process all the messages by by 1/4. Right? So therefore, by adding more consumers, we can actually scale the system horizontally. Up until now, we've been dealing with just the publisher, consumer, and the queues. But with RabbitMQ, there's actually another component to the messaging system, and that is the exchange. Okay, before we say that the publisher sends a message to a queue, but in RabbitMQ, the publisher actually always sends a message to an exchange, right? And then the queues bind to that exchange. So there's some binding that is declared, and then that's how the messages go from the publisher to the consumer. Again, the publisher publishes the message to an exchange, and the queue is bind to an exchange in order to receive those messages. And then from there, the consumer consumes the message from the queue. RabbitMQ implements a protocol called AMQP, and that's how the exchange gets introduced. AMQP. So AMQP stands for Advanced Messaging and Queuing Protocol. And this protocol is different from the traditional JMS, which only defines the 3 elements that we saw before: the publisher, the queue, and the consumer. And with the AMQP, they actually introduce a new component called the exchange. Now in the AMQP, it defines different types of exchanges, but the most common ones that we'll be dealing with in this video is going to be FanOut, Direct, and Topic. So each one of these defines the behavior of the exchange with respect to how the messages will be routed from the exchange to the queues. Okay, using exchanges, you can create a PubSub system. So PubSub stands for publish and subscribe. Okay, and what that means is I have an exchange and I have a publisher that will publish messages to that exchange, and then you can have more than one consumer. So let's say I have a consumer 1, and then I can have another consumer. Okay, and when the publisher sends a message to the exchange, that message can go to more than one queue, right? So in this sense, that's the queues are subscribing to the messages from the exchange. Okay, so the first type of exchange that we're going to talk about is the FanOut. The FanOut Exchange. Okay, in a FanOut Exchange, all the messages will go to all queues. So when the publisher publishes the messages to exchange, those messages will get delivered to each queue that is binded to that exchange. Okay, so next we're going to talk about the direct exchange. As we said before, a publisher publishes to an exchange, and the consumer consumes the message from a queue. Now, in order for the system to work, the queue has to be listening on the exchange. The way that it does this is there's a way to bind the queue to the exchange. When you bind the queue to exchange, you have to specify a binding key. Now, this is something like a filter that is specified that's going to be used by the exchange to figure out if the messages should go to that queue. Okay, so the binding is really just a string that specifies. So, for example, a binding could be, I can say apple, and then here I can say orange as an example of a binding. Okay, and when the publisher sends a message to the exchange, it has to specify a routing key. Okay, the routing key is also a string. So the way that the exchange uses the routing key is to match the routing key to the binding key to figure out if it should send the message to the queue. So in this, for example, in this case, if let's say the publisher specifies a routing key of data, right? So now the Q1 has a binding of apple and Q2 has a binding of orange. So in this case, when the message gets published to the exchange, neither of the queues will get the message because the routing key data doesn't match any of the binding key and binding criterias. Now, if the routing key was apple, right, then that message will go to the first queue, and it doesn't go to the second queue because the binding for the second queue is orange. If the routing key was orange, then that message will go to the second queue, but it doesn't go to the first queue. So in summary, we can use the bindings to filter messages that are coming from the publisher, and the way that we do that is basically using the routing key. Right. So in a direct exchange, the only way that the messages get to a queue is if this routing key is equal to the binding key. Right. So in this direct exchange, routing key must equal to the binding key. The binding. Right, so that's basically how the direct exchange works. So what is the difference between a fan-out versus the direct exchange? In a fan-out exchange, we always deliver messages to the binding queues, regardless of bindings. In a direct exchange, only deliver messages to the binding queues when the routing key matches the bindings. So in a fan-out exchange, you can specify a binding, but it will never be used. Likewise, with a routing key, you can always specify a routing key, but it will never be used in a fan-out exchange because, again, in a fan-out exchange, all messages will be delivered to all queues that are binded regardless of the routing key or the binding key. But in a direct exchange, it uses the routing key and only forwards to the queues if the routing key matches the binding key. Now, if you want something in between, that's when we start to use a topic exchange. With a topic exchange, you can have more freedom in specifying the binding keys. You can use wildcards to specify a pattern for the binding keys. And you actually have two choices. One is you can use a star, which can substitute for exactly one word. You can use a pound or hash that can substitute for 0 or more words. So in the picture below, I have 3 queues and each one has a different binding. So for the first one, I have shape and then with the star. So that will only match when there are 2 words specified in the routing key. For the second binding, I have a shape and then with a hash or a pound, and then that can match one or more words. Right. So each word is separated by a period or a dot. Right. And the third binding is just one word, shape. So that means it has to match exactly that word because we didn't specify any of the wildcards. Now, if you specify only a word, like in the last binding, that is really just behaves like a direct exchange because it has to match exactly with the routing key in order for the message to be delivered to that queue. Okay, so let's take a look at an example. So here, let's say that I have my routing key as shape. And then that will be delivered to the third one. And also, it will be delivered to the second queue, but it will not be delivered to the first one because the first binding requires the routing key to have actually 2 words. Okay, so that's the difference between the star versus the hash. The star must match exactly one word. So therefore, if the routing keys only doesn't have that pattern, then it's not going to match. Whereas the pound or hash can match 0 words, right? So that's why the shape can actually go to the second binding. If the routing key was shape, and then say circle. Now this routing key will go to the first and the second, but not the third, because the third one only needs to match one word, and in this case we're specifying 2 words in the routing key, so that's why it's not going to pass that filter. Okay, so that's basically how you use a topic exchange. Now, one thing to note is that you can specify these wildcards in front of the word. So in for example, I could say, I could have a star and then dot and then say shape and then dot star. Okay, in this case, I'm expecting 3 words in the routing key, but the middle one has to match shape. And then the other thing to note is that if your binding is only this, has a hash, which means 0 or more words, then this acts like a FanOut exchange, because regardless of what the routing key is, that message will always be delivered to your queue. So that's all for this video. I hope you learned something from it. Thank you.